So chapter 6, fossil fuels. Now we're getting into an area that a geoscientist might be a little more comfortable than talking about the electrical grid. So that's nice that we get to talk about things that we're more familiar with for a change. All right, so this is a lot of what's out there. There's a lot of politics about fossil fuels. So here's one: unless the age of fossil fuels ends now, our world will. And I couldn't disagree more with that statement. There we have a skeleton pumping gas. Break free from fossil fuels. Interesting. Dandelion seed breaking a chain. Very interesting. Keep it in the ground. And there's a lot of negative opinions about fossil fuels, oil, natural gas, and coal. And I think we can understand why. It's got to do with climate change and air pollution and some other things. And the general, let's say, less than appealing profile of certain wealthy oil people. But let's see and let's look at fossil fuels from the perspective of the portfolio of energy sources that we need to maintain our civilization. So let's talk about the global energy supply today. Today, it's more than 85% fossil fuels. So here we've got the US, so natural gas, 33% of total energy, petroleum, 36%. So that's transportation focused. This is electricity focused. Renewables, 13%, coal, 10%, nuclear, 8%. That's for the US. For the world, coal is, this is, I don't know how many, 620 exajoules. So that's 164. Oil is 196, natural gas 144, nuclear energy 25, hydroelectric 40, and other renewables 51. So, this is the renewables globally, and these are the renewables in the United States. It's a fraction of the overall energy demand. And the book doesn't spend much time on the fact that 85% of, or 90%, somewhere up there, of the energy we require for civilization are fossil fuels. So here we're looking at sort of the growth of let's see, what is KTOE, kilotons of oil equivalent. As you know, the units of energy can be quite baffling. But chapter 6, got a whole 2.5 pages on coal, and to be fair, they have 2.5 pages on natural gas and a whole 2.5 pages on oil. So we're going to try and cover this in a little more detail than the book has done. So here we're looking at two of the growing economies, China on the left, India on the right. So you can see the tremendous growth in energy use in China from basically, what is that, 500 terawatt hours in 1985 to, 9,000 terawatt hours in 2022. And this curve just keeps going up. And you can see that coal is a big part of it. China is a world leader in renewable energy, in wind and solar and hydropower, but still, China is a coal-fired economy. India, which is not using nearly as much energy as China is, but is growing rapidly, they are also a coal-fired economy, almost 60%. Now, one of the interesting things is what's happening with the way ERCOT is generating electricity. So here we're looking at just the last, less than 20 years. In 2006, natural gas was 46%. Coal was 37% of the electricity in Texas, right? Wind was 2%, trivial. Nuclear was 14%. Now, nuclear hasn't changed. We've always had these two power plants. That hasn't changed. Well, the reason it's gone from 14% to 9% is because the amount of electricity that's generated in Texas has increased proportionately. And then look at solar's coming in. And the solar is growing fast. And it's growing faster than wind did. Wind went from 2% to 10% in 7 years. Solar went from 2% to 10% in 4 years. So you see that today, the amount of electricity we're getting out of the proportion of our ERCOT electricity is about the same for natural gas. That's basically double, well, not quite double the amount of electricity today that it was in 2006. But coal is getting squeezed incredibly because wind and solar are penetrating, and that's stressing the grid the way that we've talked about it with the duck curve. That they don't really talk about it much at ERCOT, but they're very well aware of it. So let's talk about the book talks about fossil fuel resources and extraction. So coal is definitely the most abundant fossil fuel. It's globally distributed and it's near the surface. So in addition, the U.S. has the largest coal reserves in the world, whereas China produces the most coal. So it's we'll see a similar difference between where the oil is and where the oil is produced now when we get to oil. Now, here's how we think about non-renewable natural resources like natural gas or oil or coal or, and minerals too, for that matter. So there's four sort of concentric circles. Total remaining in place, that's the theoretical limit of the resource. If cost was no object, all of this would be available to extract. Then there's the technically recoverable resources, both economic and non-economic, right here. So these two don't change. They're not sensitive to economics, but economically recoverable resources are. That can get, if the price goes up, this ellipse will increase in area. If the price goes down, it will decrease. So these economically recoverable or profitable resources, that's the present economic limit of the resource. And the proved reserves, that's basically been quantified by geologists and engineers at a particular site, either one that's being mined. It requires a lot of work to do that. Okay. So, for example, in 2025, the U.S. had 3,871 trillion cubic feet of total technically recoverable natural gas, this area. And shale gas was 58% of that. And the total future natural gas supply, including reserves and resources, this one is 4562 TCF. Now let's look at the levelized cost of energy again. We can talk about coal. This is the recent one, and you can see that coal is. This is where you want to be if your company wants to make money, is wind, solar, natural gas combined cycle. Those are the three legs of the stool of the U.S. Texas energy stool. Geothermal is very useful, but it's not everywhere. So, offshore wind is more expensive, and coal is right up there. The only thing that's more expensive than that is nuclear and natural gas peaking, which isn't used very much, only to fill in when demand is high. So that's the main thing that's happening. Now, here's where politics and economics collide. So here we got Trump receiving a shiny trophy as he's named the undisputed champion of beautiful, clean coal by mining executives at the White House. And he's pushed this a lot, but the fact of the matter is, it doesn't matter what he's pushing. So here he was pushing coal in his first presidency, and the total U.S. coal consumption by the major end user decreased by almost half during his presidency. if his presidential exhortations or anybody's presidential exhortations had anything to do with demand, this curve would have gone like that, wouldn't it? And I can't think of a better example of just how confusing it can be to listen to people, politicians talk about energy, and then compare that with the reality of what's happening. And Texas is an extremely good example of that. You know, we don't quite have people who would be qualified to be the undisputed champions of beautiful clean coal or oil or natural gas in Texas, but we've got a legislature that is not particularly sympathetic to renewables. But the reality is, in the battle between financial gain and politics, people are always going to go with financial gain for good reason. All right. So back to coal. Half of the world's coal is being used by China now. So you can see here, this is China's growth in the use of coal. India is growing too, but not nearly as much. The United States, on the other hand, is using less and less coal all the time. So how do we make coal? So coal forms in ancient swamps and bogs, and it powered the Industrial Revolution of the late 18th and 19th century. One of the realities is the carbon content of the coal, and thus its energy content per kilogram, increases as it is compressed and moisture is removed. And the first type of coal to form is lignite. And then the next one is subbituminous coal, then bituminous coal, and lastly, anthracite. So these grades of coal, which you could think about as metamorphic rocks, right? Whereas the lignite would be basically just barely starting to alter from peat, whereas anthracite is basically a metamorphic rock. And so, you know, if all things were equal, which they're not, you would want to use anthracite. So here's an example. We won't read it all, but lignite, the lowest rank, contains 25 to 35% carbon, subbituminous, 35 to 45% carbon, bituminous, 45 to 86%, and then anthracite, almost 100% carbon. So, but now look at the production numbers. Lignite is counted for 8% of the total U.S. coal production, and you know, that's Texas coal, which we'll talk more about. Then subbituminous was, you know, about half of the coal that's used in the United States is subbituminous, and most of that was produced in Wyoming. Bituminous coal accounts for about 48% of total U.S. coal production, and these are mostly in the Appalachian states. And then finally, anthracite. Only a few places where you can find that are in northeastern Pennsylvania, and it's, you know, very small amount of that is being used, and mostly by the metals industry because of its high, very valuable properties for coking. So here are the coal deposits of the United States. So we're also going to talk about coal bed methane. So we're showing that as well. Coal bed methane is generally associated with coal fields, but you can see that there's the Powder River basin. You know, a lot of coal in Wyoming. You know, Utah, a little bit in Colorado, New Mexico, quite a bit in Texas. We'll talk a lot about this. Lots in the Appalachians, right? So within the United States, Wyoming produces the most coal. And the reason for that is it has a low sulfur content. And I remember used to drive to UTD from 75, come over on Campbell, and I'd be stopped, you know, as a coal train from Wyoming came across. And what they do is, you know, we've got plenty of coal in Texas, but it's relatively high in sulfur. So they would actually mix Wyoming coal with the Texas coal to get the overall sulfur content down. Sulfur is bad because it causes acid rain. Today, almost all of the U.S. coal consumption is for electrical generation. Now here we have the Texas coal mines. So it's all in this East Texas belt. So there's but basically as we go as sort of east from Dallas, Dallas is about dookie right there, right? Fort Worth, that's Tarrant County, that's Dallas County. And as you go over towards Louisiana, you go across this big belt of Eocene rocks, right? These are the rock names, the Wilcox Group, the Clay Barn, and the Jackson. And that's where the coal is. And what they would do, back when we were using, a third or 40% of Texas electricity was being generated by coal, they would build a power plant right next to an open pit mine. So the transportation costs were very small. But the problem is it's all lignite. Lignite's the sort of the least valuable coal, but they can be strip mined. So that's relatively easy to do. So there's two ways that we mine coal. One is by strip mining. So that is for your low grade and your subbituminous coal. It's less than 200 feet deep. It's cheaper and safer. You don't have things collapsing on you. Whereas underground mining for the higher ranks, bituminous and anthracite, this is more dangerous and expensive. And most of the coal in China is underground like that, and that's why they have hundreds, if not thousands, of deaths in coal mines every year. And obviously, if you're in that environment, there's a lot of coal dust. There's a problem with black lung disease and a lot of other problems. Whereas out in the open like that, you're not breathing the dust as much. All right. Now, one of the interesting things about Texas coal is it's got a lot of mercury. So, and mercury causes serious health problems. The Mad Hatter in Alice in Wonderland, he was mad because they used a lot of mercury to sort of finish hats back in the 19th century, and obviously came in a lot of contact with mercury, and that's why we get the saying "mad as a hatter," right? Because that was a serious problem back when people were messing around with a lot with mercury. So 5 of the coal-powered plants with the highest amount of mercury emissions are located in Texas. So that is a reason why we don't really want to use Texas lignite, even though it's here. All right, UTD and coal. So UTD, those of you that have had the pleasure of meeting Bob Finkelman, he's in the Geosciences department. He's a coal expert, and comes in, I think, once a week these days. A lot of times he's down using the SEM lab. So introduce yourself to him and ask him questions about coal. He's a world famous coal researcher. And then another link is Naveen Jindal, who was the chairman of the Jindal Steel and Power Company, and is also gave $25 million a few decades back to endow the business school, management school, which is called the JSOM, the Jindal School of Management, or JSOM. And he was indicted. Now, this is an interesting one. He was indicted with 4 other officials in connection with the allocation of some block of coal that in India, and I don't know what the state of that court case is, but UTD's got a pretty good connection with coal. All right, so now coal is going away. We've looked at these energy transitions sort of in the introduction, and you can see that in 2019, renewable electrical generation crossed coal generated. So, and this just keeps going up, and that just keeps going down. This one is interesting. So what we've got here is 2023 utility scale electricity capacity. On the left, these are the planned additions. They're planning a total of 56 gigawatts that was going to be added in the United States. So you can see that it's, over half of that is solar, almost all photovoltaics, batteries, natural gas, wind, nuclear, and other, very small. And the power plants that are going to be retired are over 60% coal-fired plants. So, and then a lot of the natural gas plants are being retired too. These are the older peaking ones, whereas the ones they're adding now are the combined cycle. So you can see this energy transition in real time. We need to learn a little bit about the Texas Railroad Commission, which is a very poorly named government agency because it doesn't really spend that much time on railroads. Okay, some of you might be interested in looking into internship and job opportunities with the Texas Railroad Commission. That's certainly something where you might consider. All right, so we're done with coal. Does anybody have any questions, burning questions about coal, so to speak? Okay, well, I think we can get started and get a little way into the natural gas story. So this is section 6.1.2 in your book. And here we're looking at U.S. primary energy consumption by energy source in 2018. Coal's gone down, but pretty much everything else has changed. And you can see how important natural gas is in the energy mix for the nation. So it's mostly methane. Natural gas is mostly methane, which is CH4. It's a hydrocarbon, but it's hydrocarbons are chains, and we'll talk about them when we talk about oil. And CH4 is the simplest hydrocarbon. It's currently the second most important overall energy source after petroleum. And the two of them sort of go hand in hand. So natural gas is the cleanest burning fossil fuel, and it is the best fuel to replace coal and oil to transition us into a future carbon constrained world. So we expect global demand for natural gas to increase by a lot in the next 15 years. And, it'll be a quarter of the primary energy mix: oil, gas, coal, nuclear, and renewables. And one of the interesting things that's happened in the time I've been in Texas is how, the shale gas boom occurred. And this is a really interesting story. And another thing is that hasn't really hit the market is methane hydrates. And we'll talk briefly about that. So just to let you sort of telegraph the punchline, methane hydrate is by far the most abundant resource of methane. In fact, the energy trapped in methane hydrate is more than twice that of all fossil fuels combined. And we'll talk more about that later in this lecture. All right. U.S. is in very good shape when it comes to natural gas. And I draw your attention to this remarkable curve. It starts in 1990, goes almost to today, not quite. This one goes all the way to today. You can see, there's been more and more production. There was a little bit of a dip during COVID, but, still going up. But look at, during the 1990s until about 2006, we're sort of bumping along at 18, 19, 20 trillion cubic feet per year. And then beginning 2006, it just skyrockets. And we begin exporting liquefied natural gas, which we'll talk about in 2016. So that is an amazing thing, from less than 20 trillion cubic feet a year to over 100 trillion cubic feet a year in 20 years later. Amazing. And as a result of these enhanced supplies, natural gas prices have been mostly pretty low since about 2009. So it was 2021, went up a bit, 2022, 23, but basically it's not changing much now. So what caused that price drop in 2008, which we're not seeing on here? Sorry. All right, so let's talk about where we get natural gas. So here we've got a schematic of the three sources of natural gas. One of them is coal bed methane, which we'll talk about. Another one is conventional non-associated gas, which means there's no oil here. The other one is conventional associated gas, where the oil's underneath, the gas cap's on top. And then there is the gas-rich shale. This is called the unconventional shale. These trapped gases in structures like oil deposits are considered to be conventional, and then coal bed methane's kind of another thing. Any questions about that? All right, let's talk about coal bed methane first. So coal bed methane, as we know, is natural gas, and it forms during the process of transforming the plant material into coal. It's generated either by, bacteria or as a result of heating, because it does get warmer with depth in the earth. Coal seams are often saturated with groundwater at high pressure, and then you basically just recover this by drilling wells into the coal seam. Right? You just drill a well down into the coal seam, and the gas flows to there. And about 7% of its natural gas comes from coal bed methane. These are the coal bed methane fields. We sort of looked at a similar map when we were looking at the coal basins, right? So coal basins, along the Gulf Coast, Appalachians, up here in the Rockies, Williston Basin. They don't all have coal bed methane. the San Juan Basin in New Mexico, and southwestern Colorado, the Raton Basin. You drive right by that on 25 if you go north up to Denver, and then up here in the Powder River Basin. These are the places where you have coal bed methane. Okay, so coal bed methane is a relatively unimportant part of the energy mix. Here we're looking at, um, overall natural gas from the United States, and you can see shale gas has grown tremendously and is expected to stay high. Tight gas, which is related to shale gas, but somehow broken out differently. Alaska's got its own category. Non-associated, that is, there's no associated oil deposit offshore. Non-associated onshore. Associated with oil, that's decreasing. And then here's coal bed methane. It's expected to increase slightly. All right. So here we are looking at the conventional non-associated gas, which is this yellow band here. You're drilling for oil, and you don't hit any oil, but you hit gas. So it's kind of a consolation prize, or it used to be. But you can still make some money if you got a pipeline that you can connect to. In many places, like in West Texas, they're just flaring the gas off, but that's associated with associated gas. So this is the way that we regard this would be your classic oil deposit. So we've got oil, right? This black stuff, it's sitting on top of salt water. This is the reservoir rock in here. And then on top is the free gas cap. So, this is sort of a textbook example of the oil associated gas, in something, like a typical oil well. If you don't drill deep enough, you're going to miss the gas. You're going to miss you're not going to get the oil. If you drill too deep, you're going to hit the salt water. And as you pull out the gas and the oil, the salt water comes in. And as you know, whenever the well starts producing salt water, it's time to cap your well or do something different. So that's sort of a very nice representation of a conventional oil deposit associated with the gas cap. So something changed in 2006, and that started gas production doubling in 15 years. So what was it? And probably most of you know. But it was the shale gas revolution. And this was something that was, George Mitchell was given full credit for it. I mean, it wasn't just him, but he's called the father of the shale gas revolution, and his company pioneered the technique of horizontal drilling and hydraulic fracturing, sometimes affectionately referred to as fracking, shales to release natural gas. And he worked this out in the Barnett Shale of Fort Worth, and we'll talk more about that. And here's an image of it if you haven't seen it. This is a simplified cartoon I made many years ago to explain the geology of Dallas, Fort Worth to people. And what you can see is all these greens are overlying Cretaceous rocks. And then underneath here, we have the East Texas Basin. We may mention that a little bit, the oil in there. And then the Texas Craton, which is exposed down in Llano down here. And then Paleozoic rocks, including the Fort Worth Basin, which is a basin that formed in response to collision with the Ouachita Fold Belt. So here's UT Dallas up here, sort of on the corner with Collin and Dallas. So this orogenic front of the Ouachita Fold and Thrust Belt goes right through UTD. And then this is the Fort Worth Basin, and you can see the depth contours. This is called the Bend Arch, and the basin is over here, the Fort Worth Basin. And you can see this is, going down, 3,000, 4,000, 5,000, 6,000, 7,000, and then what is that, 8,000? It gets really, really deep here. So that's what Mitchell was figured it out with. All right, so here is the shale gas. Now we're looking at the Fort Worth Basin, right? There's Dallas. This is called the Munster Arch. It's not an arch. It's a different structural element. And these are all of the natural gas wells that have been drilled in there. And what you can see is this is a Barnett Shale gas production and a rig count. So this is vertical. They just drilled vertically to get this gas. And then when they started drilling horizontally, beginning around, what was that, 2002, 2003, this just exploded. And it reached a peak around 2008, and it's fallen off since then. And you can, so this is the total gas production, and it's on a decline curve now. Now you'll notice here that this is plotting two things: the cost of oil, West Texas Intermediate in dollars per barrel over here, and natural gas in dollars per, I forget, trillion cubic feet or something. And you can see that, notice mostly they track each other until about the late 2000s, when all of a sudden oil and natural gas, that's oil, that's natural gas, they diverged. So instead of following each other, gas got a lot cheaper while oil continued to get expensive for the most part. And that's just how successful this revolution was. So we're dealing with this kind of a natural gas reservoir. This is a gas-rich shale. It conventionally, with the horizontal vertical drilling, you wouldn't be able to get much out of it. It wouldn't be economic. But with this horizontal drilling and fracking, it's economic. So let's talk a little bit about the geology of what's going on. Traditional oil wells go straight down to tap fluids that are sort of in some kind of a trap. And for decades, we knew that shales were there were source rocks for hydrocarbons, oil or gas, and that which was the oil and gas formed as organic matter was cooked over millions of years, mostly in the shales. And in conventional systems, oil and gas could only be extracted if they had migrated to something we call a reservoir rock, which was typically sandstones, which have a lot more porosity than a shale. So this is the source rock. This is where the hydrocarbons are generated, and then they have to migrate over to here for a conventional oil and gas reservoir. And what the problem is porosity, right? If you've got porous, permeable thing like a sandstone, the gas or oil can move, can migrate. But if you've got something that doesn't have any pore space or has micro pore space, like shales, then you can't get it out. And that was what the hydrofracking did. It provided porosity. And what the horizontal drilling did was it allowed a very long section of this shale that's buried to be tapped. Any questions about the importance of porosity and permeability in oil and gas, or any kind of fluid extraction? Okay. So the shale gas revolution. The shales have, as we said, have negligible porosity, and this are not what we call conventional targets. But George Mitchell wasn't the only person that did this. He just took the pieces together and applied the resources needed to refine the technology and make it economic. Yes, Clint.
Right. Yeah. The fracking became something people knew about after the shale gas revolution, but it had been people had been doing it for almost 100 years, beginning with like actual lowering nitroglycerin into the hole and blowing it up.
Yeah.
And then later they realized, okay, well, if you've got a hole 5,000 feet deep, then the water pressure in that, in that tube, if you fill it with water, that's going to be the same pressure as 5,000 feet under the ocean. So it will push out into the rocks. And so fracking has been done for many, many decades, but it only became a thing once it started happening in people's backyards.
Well, the horizontal drilling was something that was relatively new.
That
That
was
that
new, and also the volume of water used in fracking,
yeah.
which is, and also the result that you have all this wastewater to get rid of, which you then re-inject, and then you cause seismicity.
Yeah. So yeah, it definitely is absolutely critical, and we'll talk about this more as we get into oil. So basically, this is the deal. So here's a well pad. There's the drill platform. You go down, hit the layer of interest. It's going to be a shale layer, say the Barnett Shale, and then you drill horizontally as far as you can, and then you frack at intervals. You put a plug in there, and then build pressure behind it, and cause the rocks to break, and then back it up, do it again. Back up the entire thing. So this technology is really quite amazing. So this is showing how it evolved, in through the 1990s. These horrors, how far they would go, and this one is, 11. That one somewhere in the North Sea, because they've got these monster platforms, and those are very expensive to build and to maintain. So if they can get as far as possible out into the source rocks, that's the best. Now, the longest these are called laterals. The longest lateral that I found about was in mid 2025. This is one that went almost 35,000 feet, or 6.5 miles. So 6.5 miles would be, how many meters is 6.5 miles? So it's on the order of 3 times 17. So it's somewhere out there.
You,
Yeah, yeah.
yeah, I was looking into this about 2005, and there was an experimental well done in Britain, and surprisingly, Britain has oil fields. You never think of
The North
jolly
Sea,
old,
very
jolly
famous.
old England as having oil fields, but they did one that was like 7 miles long just to see if they could do it.
Yeah,
And
yeah.
yeah,
I
you
think that's
can, but it's
probably it.
a real pain.
Yeah, no, yeah, well, absolutely. But I mean, now the North Sea is a very famous oil province, and it's shared between Norway, Denmark, Netherlands, England, Scotland. Excuse me. And so the result has been the 20-year-old shale gas revolution. So here is in 2009, we were producing a total of, what does that look like? About 10 billion cubic feet of natural gas today. And today we produce almost 10 times that much. And then one of the things to keep in mind, 4 of the top 11 gas producing US shales are in Texas. So that's the Permian, that's the Haynesville. That's not the Marcellus or the Utica. There's the Eagle Ford, and the
And the other one
Mississippi.
you labeled with Texas.
Oh, Barnett. Yeah. Yeah. Look at your notes, Bob. So yeah, this is one of the reasons Texas economy is doing well. All right. So, Texas has benefited tremendously from the shale gas revolution, as has the U.S. economy in terms of jobs and energy prices. And our energy security has benefited tremendously from Texas natural gas production. Don't let anybody tell you otherwise. All right. So this is the natural gas footprint. If you want to sort of see the system I mean, there's some in California and other places as well, but this is the big one, right? There's Texas on the Gulf Coast, and then gas fields in Kansas, Oklahoma, and that's power that's supplying the Pacific Northwest. And then this huge field here in Pennsylvania, the Utica Marcellus. Pennsylvania is a huge natural gas producer. New York is not, because they've banned horizontal drilling and fracking. So that's just the way it is. All right. So here we got the top 10 natural gas producing states as of 2023. Texas way over there. This is the production growth as a percentage of U.S. production growth over that 10 years. So Texas has grown on the order of 25% and now is producing 12.5 million cubic feet. I'm not sure whether that's a year, probably a year. But look where Pennsylvania is. Nobody would have thought that, rich hydrocarbon people in Pennsylvania, Louisiana, West Virginia, New Mexico. And you can see that this growth in the Pennsylvania, in the Ohio, Pennsylvania, basically the Marcellus Shale area is growing really very rapidly. And this is very fortunate for the Northeast because there's a very ready market, especially these days up in the Northeast. Okay, so natural gas in production in Texas is, as we know, we're leading the nation, producing about a quarter of all of the natural gas. In 2024, there were 85,000 active gas wells in the state, according to the Railroad Commission of Texas. But most of it is production is down in the Eagle Ford and the Permian Basin and the Barnett Shale, and also offshore in the Gulf of Mexico. So book doesn't talk very much about pipelines, but these are very important because you're not, that's the best way to get it. You extract it. Sometimes that involves imports. You process it. You'll store it. Maybe you liquefy some of it, and then it goes into the sort of the consumer stream for industries, commercial, and residential. And these terms, upstream, downstream, and midstream, we'll see this in natural gas, but we'll also see it in oil as well. All companies, not all companies, but many companies, they subdivide between the upstream, the sorts of things the geologists do, and the downstream, which is the sorts of things that any salesperson for a consumer good would be involved with. So here is the map of U.S. interstate and intrastate natural gas pipelines. So you can see, all roads lead to Texas. So interstates are regulated by the U.S. government. Intrastate are not. So there's this, people want to be one or the other for their own reasons. Mostly people want to work with their local state government rather than the federal government. All right, so these are some major. Yes, question?
Yeah, go back one. And just like a chart of your body, how you can see your veins and arteries. Oops, you went back too far.
Yeah, let me do it again.
Slide 49. There we go. Just like a chart of your body, you can kind of tell where the organs are by the concentrations of nerves.
Where the blood is.
This shows where the sedimentary basins are. And you can see Texas, the Permian Basin in the west, the Anadarko Basin in Texas and Oklahoma to the north, the Gulf Coast Basin, etc.
Good point. Yeah, this is very geological. At least there's a geology layer under here that's not being shown. All right, so the major oil companies, natural gas companies in the Dallas-Fort Worth area, potential employers for some of you, is Atmos Energy. That's the largest natural gas pipeline company in the Dallas-Fort Worth area. It's got serves over 1.5 million customers, vast network of pipelines, and this is mostly, it's got a very strong intrastate pipeline system, and they own and operate 5 underground gas storage facilities. A couple other companies, Energy Transfer, that's a company in Dallas, operates 140,000-mile network of pipelines across the U.S. This, including pipelines specifically designed to move natural gas from the Barnett Shale. And then Kinder Morgan operates the North Texas pipeline, which serves electric generation facilities in the DFW area. All right, now natural gas in Europe has come into the news because of Russia is a great source for natural gas, and Europe is a great customer for natural gas. And then, 4 years ago, I think yesterday, the war with Ukraine started, and they started shutting that down. So look here, this is the share of Russian gas in EU gas demand. So 30, 30, 30, then it goes up to 45 or 50. The Germans shut down their nuclear power plants, or wanted to, and then all of a sudden the war started, and Europe has stopped relying on Russian natural gas, and that's created something of a problem. Certainly, you can imagine higher prices, but also people thinking about now we need an ability to keep our electricity on. We can't rely on renewable energy yet, and so this is there's geopolitical implications for these pipelines where they cross national borders. And then you may have heard about the fact that the Nord Stream pipeline was destroyed. That's the gas bubbling out. When they built this pipeline, the Nord Stream, which comes down through here, from St. Petersburg down to basically Bremen, I think, the United States was against it, and they thought that Russia would use this to hold Europe hostage. And it was actually one of these times when U.S. policy was useful, because they didn't hold Europe hostage, but Europe nevertheless stopped using nearly as much natural gas. And I think they're still looking into who caused the explosion. But anyway, so the book doesn't talk about pipelines. It doesn't talk about liquefied natural gas, but this is increasingly important. And the reason for that is liquefied natural gas takes up 1/600th of the space of natural gas. So like what is that? Like 0.2% of the volume of, natural gas if you liquefy it. And so you've got a liquefied natural gas container ship, and you do this by chilling the natural gas to minus 162 degrees centigrade. So that's what you call cold. So here we're looking at U.S. natural gas exports, over from the 2015 to basically today. So, back in 15, we were already on this rise, right? 2015, we'd already gone from there to there, from 10 to 40. So there was an excess of natural gas in the United States. So, we were already there. And so we used pipelines to export natural gas to Canada and Mexico. And then beginning around 2016, we start seeing liquefied natural gas being shipped from U.S. ports. And look how much this has grown. It's really quite amazing, the growth of this industry. And fortunately, we had those plants there on the coast, which were designed to bring in liquefied natural gas, at the end of the last century. All you have to do is just modify them a little bit and use it to ship it. So here's what you need to liquefy these big LNG processes and equipment, big refrigeration systems, compressors, drivers, refrigerant condensers, an evaporator. Very in conceptually very similar to what your air conditioner does, but your air conditioner makes it cool in your house by expanding liquid, and this is basically using energy to compress the gas into a liquid, condense and chill it. Okay, now I want to talk very briefly about methane hydrates. Methane hydrates, sometimes called methane ice. This is a future resource, and this is the structure of methane hydrates. So these are water molecules, and inside of this sort of framework mineral of methane of water ice is trapped a larger methane molecule. So this is ice that can burn. So you sometimes hear these methane hydrates called methane clathrate. Clathrates are something that looks like that.
Wait, there's no Y in it.
Oh, you're right. Clathrates.
It's just a clathrate.
Thank you. All right, so here we're looking at sort of the volume of methane in methane hydrates and other conventional and unconventional gas resources. So conventional gas, basically, you're drilling into some kind of a trapped gas pocket. Unconventional, we've been talking about that, and then this is the methane hydrate abundance. So this is basically one way people think about methane hydrates are a research topic in their own right because they occur in Arctic regions, near the surface on land, and they also occur in the submarine environment. So here you can see this is the abundance of them on land, and then different places you find them under the ocean. So this is a complicated diagram, but it's useful to think about. So this is water depth, sort of from 10 meters below the surface to 10,000 meters below the surface, but basically the Challenger Deep. So most of us, we're not going to worry about that deep. This is sort of the interval that it likely to be economically exploited. And then here's temperature. So here we've got methane gas and water when you're shallower and warmer than that, right? So you're in shallower water, or you're in very shallow sediments at that depth, but the pressure is quite low, right, over here. And as you go deeper, you have the methane hydride stability field, this purple area. And then this is the geotherm, basically the temperature structure inside the earth, right? It gets warmer as you go deeper. So this is shallower, lower pressure, colder near the surface of the ocean. And this is deeper, higher pressure, warmer areas of buried sediments, right? So you basically have a region where below which methane hydrates are stable, a region in the sediment column. So here we're looking, oh yes, Clint.
Yeah, and just to point out again that this is, even though we're talking about 0 degrees, and you don't think of Houston and Galveston as like freezing cold, but off in the Gulf, the deep waters are very cold. And so that methane hydrates exist, in fact, off in the Gulf of Mexico.
Yeah, well, in fact, that low temperature of the world ocean is everywhere, not just the Gulf of Mexico. Once you get below the surface.
Yeah, I know.
Well, I'm just explaining for the rest of the class. Anyway, it is complicated. When I first started seeing this, I was confused. So here what we're looking at is a VAMP, a velocity amplitude pull-up. So basically, you see these are the reflectors, but you see they go down where the methane is flowing. So that's the kind of structures that people are looking for. Now, what is BSR? This is called the bottom simulating reflector. And when it's called that because people didn't understand what they were seeing. They were seeing this reflector that was in these sediment columns offshore that strongly looked like the bottom, but it was too deep. So that they called it BSR, bottom simulating reflector. And that's the shallow limit and that's the deep limit. And this region in here is where the methane hydrates are, the methane ices are. Does that make sense? Geophysics. Ah, that's why I like this one.
Methane hydrates have fascinated the community for decades now. This stuff is cool. So methane hydrate is a combination of water molecules and methane, where the methane sits inside a cage of these water molecules and it forms at high pressure and low temperature. The methane hydrates that we commonly talk about are in the Arctic and the other very common places on continental margins. So as you go into the offshore, the combination of cold water and high pressure leads to a province of methane hydrates. Methane hydrates are a huge potential energy resource. There's an estimate that there is 7,000 trillion cubic feet of methane available in these hydrate reservoirs in the Gulf of Mexico alone. To give you a sense of what that means, that's 250 years worth of gas given our present consumption rates in the United States. So it's a tremendous potential supply. The problem is how to produce methane hydrates economically and environmentally. We don't understand how the material behavior of these rocks changes as we produce them. If you take that methane hydrate from depth and you don't control the pressure and the temperature, it's going to disassociate. The majority of it has just bubbled off into the atmosphere as you raise that rock. One of the most fascinating challenges of this project is to be able to drill and sample these hydrate deposits. We're drilling a hole in a mile of water, and then we're drilling a hole almost 1,000 meters below that. You've got to go down to that area. You've got to take what we call a core, a small cylindrical sample of the rock that has methane hydrate into it. And while you're down there, you need to seal that sample inside of a pressure vessel, like a pressure cooker, because that sample is under pressure and you have to safely store that sample for further analysis. Look, in the United States, natural gas is revolutionizing our energy supply. We're using more gas instead of coal. We're lowering CO2 emissions. And here's a resource where we know there's tremendous amounts of methane of natural gas stored. And we want to explore the potential for that as a fuel of the future. The University of Texas is taking the lead of actually sampling these potential hydrate reservoirs in the Gulf of Mexico. At the Jackson School and at UT as a whole, we're committed to making fundamental advances. And we're also excited when there's potential for those advances to have societal impact. A better understanding of the methane hydrate resource has the potential to change a lot of lives down the road.
Okay, so this is sort of showing where the methane hydrate stability sheet is. So here we're up in the Arctic region on land. So the methane hydrate layer is very close to the surface, and as we go into the offshore, it's subsurface, depending on water depth, which is pressure, not so much on temperature, which basically is constant once you get below about 1,000 feet. All right, so the technical challenges that are impeding the exploitation of methane hydrates is captured here. So, you've got all this methane hydrate. This is a drill hole. So, how do you liberate the gas from the ice? And here what's going on is either injecting hot water to raise the temperature, and that will break down the ice and allow the gas to flow into the pipeline like that. Um, this one is basically showing the same thing. Another idea is to inject CO2, which could CO2 makes a hydrate, a clathrate as well. So it could be that if we inject CO2, we can liberate the methane and sequester the CO2. Something to think about if you're interested in that topic. Okay, any questions about natural gas? It's we'll talk about a lot of things in this class. Some of them are depressing, some of them are make you feel good about the future. Natural gas is one of the things that makes you feel good about the future.
You.
Yes,
Well,
Clint. Yes.
And one thing about natural gas is that you get all kinds of gases, and sometimes you get gases that you didn't expect, like helium, which is useful. And another thing, just to remind you that we talk about is natural gas is kind of like reduced harm. Like the British government recommends that people take up vaping instead of smoking cigarettes as a measure of reduced harm. And that's one thing that burning natural gas does, especially in the combined cycle plants. I'll shut up.
Yeah, and this is an important point. Is there's fossil fuels. We've made this point several times that coal in terms of the energy density per unit mass of coal generates less heat and more CO2 than the same mass of natural gas. And that's a key point. All right, so now we're going to talk about petroleum, oil. So this is very important. This is total U.S. primary energy consumption by energy source. We're starting to understand that natural gas has the lion's share of electricity generation and growing. Petroleum, on the other hand, has the lion's share of transportation and growing. So we're going to switch gears a little bit to talk about oil. And there's, Texas is a good place to start. 160,000 active oil wells in the state, with typically 200 to 300 drilling rigs operating at any one time. So here we've got a very interesting comparison. The distribution of global oil reserves in 2019, basically the same as today. And this is the top oil producing countries. So I want to draw your attention to two nations. One is the United States and the other is Venezuela. So the United States is by far the most oil producing country in the world, far beyond Saudi Arabia and Russia. It was in second and third place. Venezuela, with the largest petroleum reserves on the planet, a little bit more than Saudi Arabia, isn't even on this list. And that's a reflection of the failure of the socialist government in Venezuela. And it precipitated, I'm sure, the U.S. Intervention recently. So another example of energy and geopolitics. Oh, I should point out that after the intervention, Trump had this big meeting with all the oil executives, and Exxon boss said, "Well, thanks, but no thanks. We've already been nationalized twice by that nation, so we're not really comfortable investing again because, as you know, companies want safe investments. They want to be able to reap the benefits of their investments, and when you're always getting nationalized, it's hard to do that." Yes, Clint.
It's really strange. It's like people in the oil business understand that it takes a stable environment to make money, and even then, it'll probably take 15 years before you see it buck back.
Yeah. All right, so let's keep moving. So again, horizontal drilling and hydrofracturing and shales is basically responsible for 250,000% increase in U.S. oil production since 2008. So just a little bit lagging the natural gas, the shale gas revolution is the shale oil revolution. So here we've got the monthly U.S. oil production. So you can see that going up and then dropping. That's because of COVID. So once COVID was over, happy days again. And then you notice 2026, it's projected that we are now over the peak. And that is basically reflecting what's going on in the Permian Basin. The Permian Basin was where most of this growth was. And then now it seems like we're saturated. We are beyond the peak. Now, this is a EIA, Energy Information Administration graphic. So this is the Federal Gulf of America. It used to be known as the Gulf of Mexico, but you can see there's quite a bit coming out of there. So this is the Permian Basin. This is something every geologist that educated in the state of Texas, if not the country, needs to know something about. It's not the job generator it used to be for our students, but still, there are opportunities. This is basically one of the most interesting sedimentary basins in the United States. And those of you that have taken Lowell Waite's course have learned quite a bit about it. And Stephen teaches a course on this as well. And this is just showing you where the oil fields are. You know, there's the northwestern shelf, the northern shelf, the eastern shelf, and then the Delaware Basin in the west, the Midland Basin in the east, and between them a high called the Central Basin Platform. And you can see where all the oil and gas well. This is the density of oil wells per square mile. You know, red is very high, blue is low. So oil is not, you know, it isn't found over in the western part of the Delaware Basin, or for some reason in the northern part of the Midland Basin in some areas. But anyway, and as a result of this important resource, we started the Permian Basin Research Lab, Lowell Waite and I, and now Nadine, Professor Agonin has joined us as co-directors. And basically, the purpose of the Permian Basin Research Laboratory is to provide information to students and interact with industry and the community, and just, you know, take a look. Just it's not hard to find online. And Lowell puts a lot of his work on here: Scurry County, producing zones, Coke County, Stonewall County, you know. Okay, so again, we have upstream and downstream in the oil business. There's the upstream, of course, is, you know, finding oil and, you know, producing it. And then midstream is transportation and storage. Downstream is refining. There's a lot more of that with oil than there is in natural gas. Midstream, you know, this is actually complicated because it's not just upstream and downstream, but there's actually two. This is upstream to this downstream, and this is upstream to this downstream. You know, this is where you and I are every few days, right? Putting gas in our car, or, you know, jet fuel or whatever. So just be aware that's what we mean by upstream, downstream, and sometimes midstream. So let's watch a video about petroleum distillation. This is a really interesting technology.
Rise through the tower and the components condense. Process is taking place. Crude oil is supplied to a furnace before the distillation tower, where crude oil is heated and vaporized, and it becomes the crude oil mixture. The vapor and liquid mixture is then fed into the bottom section of the tower. The feed section is the hottest point in the distillation tower and can reach as high as 400 degrees C. Components that are still liquid at this elevated temperature become the tower's bottom product. Components that are in vapor form rise up the tower through a series of distillation stages. The temperature decreases as the vapors rise through the tower and the components condense. The yield from a distillation tower refers to the relative percentage of each of the separated components, known as product streams. Products from the distillation tower range from gases at the top to very heavy, viscous liquids at the bottom. In all cases, these product streams are still considered unfinished and require further processing to become useful products. Light products. Light ends are further separated into propane, normal butane, and isobutene. This stream is often referred to as liquefied petroleum gas, LPG, and is sold as a cooking and heating fuel. Naphtha could be blended into motor gasoline, but is more likely sent to a catalytic reforming unit for octane improvement. Kerosene is generally treated and used as jet fuel. Heavier distillate streams are also treated and blended into finished diesel fuel or home heating oil, or are further processed in conversion units such as fluidized catalytic cracking and hydrocracking. The routing of these streams will vary as product demand changes to either maximize diesel production or gasoline production. Lowest end of columns, asphalt.
Okay, so kind of
Distillation.
useful to know what those things are. A little bit about the price of oil. So there are spot prices versus futures prices. So the price of the spot contract reflects whatever the current value price of the oil is. Basically, you know, you're paying spot price for your gasoline, not, you'd like to have a futures contract for your gasoline, but that hasn't happened for the consumer. This is for, you know, big users. Futures contracts, say an airline would argue, would negotiate a futures contract. So it's basically an agreement between a seller and a buyer to sell or buy a certain number of barrels of oil at a predetermined price on a predetermined date. So when the futures are purchased, the contract is signed and secured with a margin payment, covers a percentage of the total value of the contract. So basically, producers and users of hydrocarbons use the futures market to lock in a price. Now, investors might buy futures essentially as a gamble on what the price will be down the road and they profit if they guess correctly. So there's two major oil contracts that are closely watched by market participants. In North America, the benchmark for oil futures is West Texas Intermediate, which is Permian Basin crude. And that trades on the New York Mercantile Exchange. In Europe, Africa, the Middle East, the benchmark is North Sea Brent crude, which trades on a different exchange. So this will show you the closing price of West Texas Intermediate, which is the spot market, right? And so that's that red line. And this is the futures price for this time. So this price, you know, would have been established sometime in the past. So you can see that if you made a bet, if you locked in a contract, say in 2021 or, you know, even into 2022, that was lower than the actual price, you could sell this and make money, right? Here, you know, sort of in 2023, the futures price is higher than the market price. So if you invested here this time, you're going to lose money. So just so you know how that works. So these are the projections for the Energy Information Agency projections for gasoline price, just very recently. So this is where we are now. And these are the prices. You know, they've been coming down a little bit. What are you guys paying for gas now in Texas? Anybody? per gallon.
256.
256, yeah. So that's, the Gulf Coast, that's about 256, maybe a little bit below. So prices are low. It's no surprise that the economy is doing well right now because energy prices are low, especially diesel fuel and gasoline. So
Diesel isn't so cheap. Diesel's in
no,
short supply. Yeah.
no, diesel is always, it used to be
It's-
cheaper than gasoline, but not
Yeah.
anymore.
Yeah.
But the price of diesel is going to track the price of gasoline for the most part, and it's been slowly coming down. And that's the projection for the future is they're going to stay low. So this is crude oil production in the United States in 2024 by state. You can just see that, Texas is by far and away the most productive. New Mexico, because they have about a third or a quarter of the Permian Basin, they're in second place. North Dakota, that's the Williston Basin. Colorado, Alaska. Alaska used to be the big thing, but not so much anymore. And so Texas is absolutely dominating this aspect of the U.S. energy industry. Now, these are the oil pipelines from Jurgen, right? Different than natural gas pipelines. And, you can see again the concentration of pipelines down here, because of these refining centers. And, I can't tell you much about that, but you've seen the Keystone XL pipeline, coming from the oil shale regions of Canada. It was gonna come here. I don't know what the status of it now is, and people making a big deal about it. But the fact of the matter is, we have pipelines coming from there. It's nothing new. It's just better one, right?
You can sort of connect the dots between the Indian reservations they go across.
Yeah. So the environmental groups have been very proud of stopping the Keystone pipeline, but all it did was move that transportation of hydrocarbons onto trains, which is much less effective. It was rather a Pyrrhic victory, in my opinion. Okay, then your book goes into fossil fuel combustion and energy conversion technologies. It talks about the heat of combustion, mathematically, and this is the energy content of various fossil fuels in megajoules per kilogram. So you can see that methane is almost twice that of coal. Anthracite is the best coal, subbituminous, from the Powder River Basin in Wyoming. Diesel is up there with methane, and so is gasoline. And then your book talks about fossil fuel use for heat and cogeneration. Cogeneration is the idea of, a company burning a fuel and using it for two things. One is to generate its own electricity, and the other is to provide heat. So, these basically steam cycle cogeneration plants. You can take the steam from a turbine, that electricity generating turbine, and use it for heat for process, for whatever purpose. And it can also be used in a combined cycle. And so the US EPA estimates there's a potential of 150,000 gigawatt hours per year, which is 12 Comanche Peak power plants if more of the industry and commercial would go in this direction. And then your book talks about electricity generation from pulverized coal. This is what the coal-fired power plants use. They don't use big chunks of coal. They grind it up into a slurry, which can actually be transported by a pipeline and then feed it into the combustion chamber and to use it to drive a turbine. And then your book talks a little bit about power plant efficiencies, comparing the average efficiencies for fossil and nuclear power plants. The heating rate in BTUs per kilowatt hour and the efficiencies there. It's highest for natural gas, petroleum and coal. Nobody outside of the Saudis uses petroleum for generating electricity. And then your book talks about electricity generation from natural gas. And they talk about these combined cycle systems, which here is shown quite simply. So here's the natural gas coming in. This is the gas turbine, which generates the electricity here that goes to the grid. But it generates a lot of hot exhaust, on the order of 1700 degrees Kelvin. And rather than venting that to the air, they recover it and use it to drive a second steam turbine. And the thermal efficiencies for these modern natural gas combined cycle power plants is 60%. Compare that with the natural gas of 43%. So you can see why everybody that is investing in electricity power plants in Texas is focused on these combined cycle plants. We got a lot of natural gas, and this efficiency is outstanding. So here's what one looks like, right? We talked about the levelized cost of energy. This is just your normal natural gas plant. This is your combined cycle. Much lower levelized cost of industry. And rather than spend a lot of time on that, let's look at a video in a minute. So the peakers, on the other hand, this is a recent term in the electricity market. So peakers are older, less efficient natural gas, sometimes coal power plants that are turned on only to meet peak demand. So, for example, a Texas summer afternoon, this is the levelized cost of energy here. But it's a more expensive. But if you already got it, all you have to do is enter into a contract with ERCOT and get on their list, and then they'll pay you extra for that and for the electricity that you generate, and it can be economic that way. Now, this is an integrated gasification combined cycle, and this starts from a solid fuel, which could be either coal or biogas. Anyway, I'm not going to spend any time on that. You got it in the book. Then there's the issue of sulfur dioxide emissions from fossil fuel combustion. So this is the total emissions of sulfur dioxide, in 2000 and 2010. China's going up, was high and going up. India wasn't quite as high, but it's going up. United States is going down, and that's because it's using less coal over this time period. And that's, mostly sulfur dioxide is coming from coal. Some of it comes from oil, but the problem is that it combines with water in the atmosphere to make acid rain, which was a problem. It's not so much of a problem anymore in the United States. So here we have a global catalog of large sulfur dioxide sources and emissions. It's an interesting map because it's got 4 symbols: oil and gas, power plant, a smelter, a volcano, right? Volcanoes put out sulfur dioxide. And, you can see these where there are volcanoes. And then the power plants here in Eastern China, India, United States. And these are the methane emissions from space. Basically, you can see where the people live and where the industrial activity is. Not so much in Africa, South America. And then your book talks about estimated greenhouse gas emissions. Yes, John?
Going back to that last slide, I'm just curious why we got so many methane emissions in Europe and some of these places that really don't have.
Well, because they've got a lot of power
Production.
plants, natural gas power plants. It's going to leak out of there. The coal. They're getting away from coal too, but this is you can see there's a relationship. That's the Permian Basin. It's not a lot of there's not a lot of power plants out there, but there's a lot of methane coming out of there. You can see there's a lot of methane coming out of this part of Middle East oil production region, a lot coming out of Ukraine.
think it burned pretty clean. You'd think it
Yeah,
burned
well,
100%, so.
yeah, there's a lot of inputs of methane.
There's leakage.
Yeah, leakage and. All right, so these are the estimated greenhouse gas emission factors for fossil fuels, which basically grams of CO2 per megajoule of energy generated. So here we've got gasoline from conventional oil, the upstream processes to get it out, the combustion, and that's the total. Gasoline from tar sands, much higher, right? CO2 emissions per megajoule. One reason to, more than the pipeline, the reason we don't want to use it. Gasoline from oil shale, it's high.